I think it's off.
Okay.
If you tap it.
Ah, wait.
Yeah.
Okay. Yes. Thank you.
Ça dépend des particules potentiellement.
Right. So we were here, and now okay. So something I would have said maybe. Okay. So this is the free energy again. This is the log of the density of this collective variable. So this low-dimensional representation of your space. And okay, here we are going to use it as an intermediary tool to sample mu. Okay. But okay, in some cases, it's a quantity which is of interest by itself, okay, because it describes the density of somehow the interesting features of the process. So okay, depending on what you want, maybe. So in many cases, in some cases in molecular dynamics, in fact, the free energy is not a tool to sample. It's really what you want to compute. Okay, and so that's just all. Okay, so now let's think again of our important sampling scheme. So we want to target a biased target, and so here is what we would want. If we put a biased potential, which is some portion of the free energy, okay, then we sample this distribution, and you see that so the density here is okay, let's say in the case where x is yz, where y is the reaction coordinate. Okay, so you have 1 minus beta u of yz minus alpha a of y. Okay, this is the new target distribution. And when you take the marginal law for y, okay, so you integrate this with respect to z. Okay. Okay, so the a here does not depend on z, so this is exponential beta alpha a of y, and then the rest. Sorry, there is that's it. Okay, and the rest is exactly the marginal law of y if you have that, which by definition is exponential minus b a of y. Okay, and so you end up with exponential beta a, but with this 1 minus alpha. So you have somehow you have changed the effective temperature at which you are sampling at least psi of x, not x, but psi of x is it has the same law, but at some different temperature. So that's the same law. And in particular, if you just take which is the typical practical use, you take alpha equal 1. I mean, at least in the initial paper, you just okay, which makes sense only if you are in the torus. Okay, this is just the uniform distribution on the torus. Okay, so you have flattened the energy landscape in the world of psi of x. Okay, so in the low-dimensional world of the reaction coordinate, you have modified that. Okay, which is equivalent to say that you have taken a temperature plus infinity in for the coordinate psi of x. And now if you look at the conditional distribution, okay, conditional distribution of z given y, okay, let's write it p of z with respect to y, okay. Now this is exponential with the biased, okay, with this biased distribution. So it's exponential minus beta u yz plus minus alpha a y, and you divide by this okay, exponential minus beta 1 minus a of y, and you see that it's again so This is proportional to that. And so it's proportional to exponential minus beta u of y z for a fixed y. So for a fixed y, the conditional distribution of the other part is unchanged. It's the same as in the equilibrium. So somehow you have splitted your joint law in the marginal law of y and the conditional law of z, and you have modified only the marginal law, and you have kept the conditional law of all the other variables as unchanged. Okay, so which seems like a good idea. In particular, if you think of this is this toy situation here. Okay, so you have modified the law of Xi, and you haven't changed the conditional law of the others. So of course now in the real situation, the two things are not independent. But okay, you get the same kind of idea. And so okay, so let's do that. End of the talk. This is the algorithm. And so we are doing the Langevin dynamics with this bias. And so because here I take these simple situations where the psi of x is just the first coordinate. So you have two coordinates and they follow the Langevin dynamics. But the first part has this bias here, and that's all. Okay, that's very nice. And okay, to do that, we just have to compute the gradient of the free energy. So here it is. So this is the log. So we take the gradient, we get this, and that's nice because it's some expectation. Okay. It's the okay. It's so again. Okay, let's take it more calmly. So when I take the gradient with respect to y of that guy, so I get the gradient with respect to y of u coming here, and because of the log, I divide by what I am differentiating here. So this is the conditional expectation of the gradient y of u with respect to this equilibrium measure, the Gibbs measure. But I only integrate with respect to this. So this is the conditional expectation of this at mu, given that at a fixed y. Okay. And just a remark, I just said that I have the same conditional distribution with the initial target measure and with the biased target measure, which means that this formula is still true. So the gradient of A is the same if you replace mu by this modified target. So as long as you just modify the marginal law of y without modifying the conditional law of z given y, you still have this formula, okay, which is going to be interesting later. Okay, so nice, we can run this algorithm by computing this. So of course, this is a conditional expectation with respect to the probability measure that we are precisely trying to sample. Okay, so computing this is like at least as difficult as the initial problem, and we have to do that at every step of the dynamics. Okay, so it's not going to be good. So of course we cannot do that in practice, and this leads to the adaptive biasing fourth method. So the ABF, it's the natural ID you want to do if you do that. Okay, so we cannot compute that. Let's replace the measure mu by whatever we have here right now, which is a good approximation of that, and that's precisely what we are building with our Markov sample. Okay, so two things you can think of, at least in terms of a mathematical way of formalism. So either you can do something which interact with its past law, so which is like doing the ergodic MCMC usual approximation. Okay, well, usually you approximate expectations as averages a long time. So okay, you can do that. So at time t, you are running your dynamics. At time t, you have an approximation of mu, which is taking ergodic averages along your trajectory. Let's do that. And so let's replace the conditional expectation with respect given y according to mu by this. Okay, so now you have some kernel here because you have a problem. This guy, okay, let's say we are in dimension larger than 1, but even in dimension 1 it would be problematic. But in dimension 1, that guy has no the probability with respect to that of a given y is 0 in general. Okay, you don't have you don't have a density with respect to the Lebesgue measure. So okay, you just do some. Okay, so here k would be something like so k of ys y would be some maybe Gaussian kernel. Okay, so you look at your sample and so a way to say that is you take your occupation measure, you do a convolution with a Gaussian kernel, you get something smooth, and now this makes sense. Now this is a conditional. Okay, no, it's not exactly what I said. Okay, writing this or taking a convolution of the Gaussian with respect to that is not exactly the same because here I normalize here. But well, anyway. Okay, so you compute, you do a single trajectory of your sample, and at time t, when you have to do the next, you have a memory. Okay, you interact with your whole memory of your whole trajectory, and you infer. So you look at all the points which were close to your current point, and you do an average over all those points of this force here. Force which you have already computed because, okay, when you do this, the Euler scheme of that guy, of course, you compute this drift, or at least you compute a stochastic gradient, maybe approximation of that guy. But anyway, you have some approximation of this anyway. And okay, if you really run that, you have computed it. So you can just keep this, you keep this integral in memory, and you keep this integral in memory, and okay, and you compute that. Okay, and the other another way to say it is to approximate mu is to say, okay, I'm going to do some mean field in interacting particles. So I'm going to have n replicas of my system, all doing that. Okay, and they are all going to interact through this through the approximation of the gradient here, which is going to be given by so again, the empirical distribution of that guy, of those guys, is going to be a sum of Dirac masses. So it's not going to so the probability that you are exactly at y is going to be 0, and so you can do a kernel approximation. And okay, so two way to do it. In fact, in practice, at least initially and in most of the development there. So initially, this was not used with a kernel. It was this gradient of A was kept in memory in a grid. Okay, so you have the like the minimal value for which you bias. Okay, let's say you're in the torus. Let's say you're in the torus. You just cut the torus in pieces of some size delta, and then you have the values of the possible values, and sorry, and you have to keep two things in each. So you have two arrays. In one array, you just count how many times you've been there. Okay, so let's call this the cell number I. Okay, this is the cell number I, and you look, okay, how many times have I been in the cell number I? And here you keep what was the force. So it's the sum over all the trajectory. What was the force applied to S given that I was in the cell number I? Okay, so again, you move and you check, okay, where is my reaction coordinate? It is in this interval. Okay, I add +1 here, and I add this to my estimator. And so now my estimator is just if sometimes later I come back here, my estimate is just this guy divided by this guy. Okay, so in terms of complexity, it's essentially peanuts with respect to the increase of complexity with respect to just doing the Langevin dynamics is very small. Okay, so it's basically as okay, you don't have to compute new gradients because what you compute here you have to compute it for the Langevin dynamics. Okay, so it's not much expensive. So of course it works in dimension 1 or 2. And then if you want to keep a grid, you are dead. I mean, okay. So this works for, yes, 1 or 2 reaction collective variable. which was the practical use up to maybe recently, and which is still the main practical use there. Okay. Right. So maybe I have to say some practical considerations. Okay, you have things to. Okay, if you have boundaries, you have things to say where you are at the boundary. But okay, let's forget that. In practice, usually the bias doesn't start immediately. You wait to have reached a sufficient number of time. Okay, you wait. If you've been there 100 times, then you start biasing. But before that, the estimator is going to be bad, and so you are going to have noise. Okay, so you have some. Okay, I don't remember how it's called. Okay, so you wait. Okay, it's when the same as when you compute MCMC estimators. Sorry, burning time. Yeah, thank you. Okay, you have some burning time. You don't bias if you haven't been somewhere enough. Well, anyway, it's some practical consideration. Okay, so why is it interesting? So it's interesting because it works in practice. This is the first point, but I'm not going to be. If I want to be honest, I cannot use this argument because I'm not the one having much practical things to say about the algorithm. So, okay, from a mathematical point of view, you can say some things which are interesting in some, of course, idealized version, which are not exactly what is done in practice, okay, because that's all we can do. Okay, so let's look at this work by Lelièvre, Stolz, and Rousset. Okay, what they say is, okay, let's take this mean field approximation, and we are going to, okay, so we let the number of particles go to infinity while sending the kernel K goes to a Dirac mass. Okay, so you think of K depending on the number of particles, and you take something like that with some epsilon n here. Okay, and you let epsilon over whatever. Okay. And you let epsilon n goes to plus infinity as n goes to infinity slowly. Like, okay, I don't remember, maybe the result is bad. I mean, it's not to 0, sorry. Yeah. Epsilons are, the destiny of an epsilon is to go to 0. But okay, it's something like, maybe it's 1 over log n, maybe 1 over log n. So there is a result by Lelièvre and maybe Stolz also and Roux. No, Lelièvre, Jourdain, Roux, where they prove propagation of chaos. But for this guy, okay, so you see, it's not a mean field in the sense that you're interacting with your local density. You're interacting only with the guys which are close to you. So you have two things. You have the number of particles which goes to infinity, and you have the localization of the interaction which converges to some Dirac. But you have to, because you need some regularity of that guy, and you cannot, okay, you have to epsilon to go to 0 slowly. So there is a result that tells you that if you start with this algorithm, okay, so this dynamics with this force, and you let epsilon goes to sufficiently slowly to 0, then you converge to that guy. Okay, so let's look at that guy now and forget this practical algorithm. Okay, so now this is something which doesn't exist in a real computer, but which is more convenient for theoretical analysis, which is the mean field limit of the previous algorithm. And now, okay, so if you have already seen something with interacting particles, so you see that when you have many particles, somehow if you take two of them, they look like independent guys, okay, because they only see the other as in a density of other particles. So the influence of one particle on the other is of order 1 over n. So they are more or less independent. So you can just say, okay, let's say they are independent. I have a law of large number. This is going to converge to the expectation of that with respect to the law of the particles. And this is here. So now this is a conditional expectation because, again, this is a conditional, this is an estimator for the conditional expectation of this guy. So now what do we have? We have again this Langevin dynamics where there is a bias. The bias depends on time, and it depends on time because it is the conditional expectation of this force with respect to, again, the law of the particle. And the law of the particle here, the particle is yz. Okay, so you have a process whose bias depends on its own law. So you have a Makin-Vlasov process, nonlinear process. Okay, and you can write another way to say it is you can write the Fokker-Planck equation for the law of rho. So first you forget that if Ft depends on rho, you write the Fokker-Planck equation of that guy. It's a PDE written on rho, and then you say with the drift Ft, which in itself depends on rho, and so you get some nonlinear PDE. So rho here is the solution of a nonlinear PDE. Okay, do you want any details on that, or? I mean, it's not going well. Okay, it's not very important. I mean, the point is that okay, we are in this idealized limit of an infinity of particles, and the very nice thing with this is that if you look at now the marginal law of the first variable, it solves the heat equation. So okay, I mean the torus again. Okay, it's so because okay, so let's look at there. You don't kill the bias. Okay, the drift. There is a drift here. And the drift is not zero because this only depends on y, and this depends on z. So even if you were converged, even if the law of rho was the equilibrium somehow, this would be non-zero. Okay, but so y is never a Brownian motion, but its law solves the same PDE as the Brownian motion. Okay, and so okay, so this converges very fast to equilibrium. This is not metastable. It's the heat equation on the torus. It converges at speed 2 pi square, which is the optimal constant of the Loxobel inequality in the torus. Okay, so this guy converges very fast very fast in the sense that it's not exponentially bad with dimension with beta. Okay, so it goes fast to equilibrium, but that's only the and that's, I would say, one of the motivation of ABF. Okay, this is the point that the marginal law of your process. So again, it's even though you haven't converged to equilibrium. So okay, there is this meaningful limit, but still you are. If you start with a law which is very far from your target, Ft is going to be very far from the free energy, for the gradient of the free energy, but still the marginal law is going to follow the heat equation. Okay, and now you have to, so that's not sufficient to say that you have converged to the target, and that's not sufficient to say that Ft is close to the free energy. But now, okay, this is the kind of, this is the main assumption that they have in this work. They assume that for each y, okay, I mean, uniformly over y, if you look at this conditional law, which is erased, but which is a conditional law of z given at a fixed y, again, either for the initial target distribution or for the bias target distribution, because they have the same law, the same conditional law. And okay, the assumption here is that this law, mu y, satisfies the log Sobolev inequality with a constant independent from y. Okay, so basically you're saying that, okay, so let's say I have this double well distribution here. Let's say that here this is y, this is z. I'm saying that if I just look at the distribution here, it's going to be, for instance, here a unimodal. Okay, I have no metastability here, and so I'm going to converge very fast. And so in each part here, okay, so the idea here is that rho should be good here. Okay, rho shouldn't be so basically rho is expected to be of the order of, let's say, the critical depths within this part. Okay, which and so even though you have metastability in y, for each y you have no in this picture you have no metastability in z, and so okay, so So you hope that rho is much better than the complete log Sobolev constant of the whole Gibbs measure. Okay, and so I spare you the details, but what the result of Leliev Stolz Rousset, the year has changed. I mean, this is the preprint and this is the publication, but I'm talking about the same paper. And now they have a convergence of the full joint law toward the target law. So the target law is the biased target law. Okay. And it also gives the convergence of that guy to the gradient of the free energy. So anyway, the convergence of the algorithm is given by a rate, which is the minimum between this rate of the convergence of the heat equation on the torus and this 1 over rho, which is this, which possibly is much better than the full Log-Sobolev constant. Okay, so somehow you get a convergence, which is somehow what you expect. Okay, you have the local mixing at a given y, which happens at a time of order 1 over rho, and then you have this, but this you have completely changed the landscape. You have just taken the heat equation, and so you have the mixing time of the heat equation. Okay, so again, if you take a stupid example like that, you can have whatever you want in so where you would have the reaction coordinate and the other guys which are independent, and those guys. So the idea is that if the other coordinates are unimodal, like Gaussian here, rho here would be just 1 over kappa, and so it doesn't scale exponentially bad with beta. Okay, if it's unimodal, it doesn't scale bad with beta. Okay, what problems? Okay, and somehow it also tells you what should be a good reaction coordinate. A good reaction coordinate, or a good collective variable, sorry, is a variable for which rho is small. So it's a collective variable such that conditionally to that, the mixing of the orthogonal of the other coordinates is fast, which can be it cannot be the case sometimes. So here are some bad situations. First bad situation. Okay, let's say I do that. Okay, this is y. And okay, you see that it's not even. I mean, let's say this is super flat, and maybe there is the global maximum is here. Okay, so it's not even metastable. Okay, you start with a distribution which is not metastable, and then I look at the log Sobolev constant of this conditional at a fixed y here. Okay, this is bad because there is a local minimum here and a local minimum here. So this guy is metastable, while the initial one was not. Okay, so you can induce metastability by conditioning here. And somehow, I mean, and okay, somehow maybe here the ABF algorithm, the previous, the result doesn't tell you that it's good, but in practice it may still be good because there is a y, there exists y, such that rho y is small. Okay, so there is a reaction coordinate a value for which the mixing is fast, and so somehow you can hope that at some point the process is going to be here, and then it's going to happen fast because you have no metastability in y. Somehow you kill the metastability in y, so you're going to arrive here fast, and so you have 1/2 probability to go back here or to go back here. So you are going to have some mixing. Yes. So I'll come back to that. My use of ABF was on cases where I did not know where were the modes, but it's not the and I haven't done super. I mean, I haven't done real world applications with that. Okay, so. And so, as I said, in some cases, people already have a reaction in mind, and so they already have some ideas of what is going to happen. But I'll come back to that because as I was in the discussion in the break, of course, this is the main problem. Of course, this is how. Okay, if you already know what is happening, you can do many things. If you don't know what is happening, you cannot just guess it. But I'll come back to that later. Sorry. Yeah. Yeah.
true for regardless of the possible variation coordinate, right? This is true regardless.
Yes and no. I mean, if you don't take this, you really want to have this, you have to put some log of the gradient of psi somewhere. You have to modify it slightly, which is what they do in this paper. They don't assume that. They have something more general, but they don't do exactly what is done in practice. They modify the algorithm in such a way that this is true. But you can always enforce that if you have a non-linear xi, which when you are saying for any xi, you add this in mind. Yes. Yeah, even if you have a bad, even if you have something bad like that, you still have this. So you're still going to sample the y coordinate very correctly. Okay, so another typical situation is okay, you have something like that. Okay, so here is one mode, and here is one mode, and this is x. Sorry, this is y, and this is x. This is z. Sorry. Okay, so what happens is, okay, you flatten here, but okay, if you go too fast, you're going to just go there and come back. Okay, and at some point here, you have the other coordinate has to change, but you don't bias the other coordinate. So it's not. So you still have some remaining orthogonal metastability that you haven't killed and that you have to overcome at some point. Okay, so you are going to do a simulation which tries to go there, but okay, possibly not in the interesting parts, and it has to wait still for something to happen. Okay, and then another situation that would be bad. Okay, basically the same as here, but let's put it like that. Okay, so the problem is I said, okay, and let's say you have a mode E. What do I want to do? Okay, let's say you have a, okay, it's not metastable, like you can go here very easily. Okay, so like you have a global minimum here, and everybody goes there. Okay, and then this is y, and this is z, and of course you don't bias on the whole space. So either you're on the torus or you get some boundary. Okay, so let's say you have the good idea to bias like that. Okay, and so you are going to sample uniformly here, but then again you are creating metastability by trying to sample something which makes no sense. I mean, which is not interesting. Okay, you are forcing somehow the. So if you don't have good reaction coordinates, you are going to force the process to sample somewhere which is not interesting again. And it's so here this is stupid problems, but so a typical case where this kind of thing is used is to do docking problems. You have a huge protein, and sometimes at some parts of it is a site for interaction with smaller molecules, and you want to see how the molecules goes here and interact with the site. Okay, and typically the what you can think of as a reaction coordinate. So you have a reaction which is coming in and getting out, is the distance between the barycenter of the interacting site and the barycenter of the molecule, say. Okay, so if it's 0, you have contact, and if it's 1, you are far. Okay, and no, sorry, that's not what I had in mind. So what you can do is add a variable which so you do alchemy. So you do something which is not physical, which is that you uncouple the two systems. Okay, you have a parameter which goes from 0 to 1. If it's equal to 1, you have the usual system, and if it's 0, okay, so you have a potential which is like okay, like you have an interaction. Sorry, and you have a parameter lambda. Let's say, okay, how am I writing that? Okay, you have some. Okay, I write it like that. You have some interaction potential. You put a lambda here. You have the energy of the first guy. Okay, you have two guys. one guy has an energy E2, one guy has energy E1, and this is an interacting energy. Okay, and if you go Y go to and those guys are different. So let's put Y and Z. Okay. So if lambda is 0, the two guys are independent, and if lambda is 1, which is what you want to sample, you have some interaction. Okay, so X is the coordinate of the protein, and Y are the coordinates of the small molecular system. And in fact, the reaction coordinate is Y. So what is happening is that you do something unphysical. You do because it's simple. Okay, you want to, and it's difficult for the. Okay, you have metastability because it's difficult to attach and detach from this. So what you do is you just cancel the interaction. Okay, the two systems become blind one to the other, and so they move freely. And when they have moved, then they can appear again, and you are good with that. Okay, so my point was that in this kind of thing, when you start, when the two systems start to not seeing each other, they go completely in a. Okay, they completely. The small molecule is going to go anywhere, okay? And then you want it to go back to the system, but it's too late. You've been in a part of the space where you have no chance to. And now you are lost in some entropic region where everything is flat and you get no. Okay, you get. It's very difficult to come back to the interesting region. So again, if you don't bias correctly, you'll have. And this can be interpreted a bit, at least in this result, in this if rho is bad here. So you can have bad situations, even in dimension 2. So let's say that in dimension 100, it's going to be, and more. Of course, you can have orthogonal problems. I mean, you can have problems in this orthogonal sampling where even rho is bad. Okay, I think that's what I wanted to say about that. Are there questions? Yeah. Yeah. Because it's a minimum. Thank you. Yeah, sorry. Yes.
And then the one.
No, so yes, you want rho. Okay, so this to be rho. Sorry, this is rho because this is the convergence of the log sub, and you have a dependency. In fact, okay, okay. What am I saying? You want rho? No, if rho is small, lambda is large, which is good because you want the rate. No, because okay, this guy. Okay, you cannot have better than the relaxation of these guys and the relaxation of this guy. But you know that the relaxation of this guy is good because it's 2 pi square. It's not exponential of beta something. It's not exponential of minus beta something. So okay, this guy is anyway good. And the question is, okay, is this guy also good? And so that's, and indeed you want rho to be small so that this is large. Other questions on this? Okay. At what time did we start again?
40.
Bon, stop me when you're the last one not sleeping. Okay, so of course there are many variations you can think of. So first, I just said, okay, if you're in the torus, you can cancel out. But of course, if you're not in the torus, you have problems to have a probability distribution. So you can add a bias here, just saying that instead of targeting either the initial target with a different temperature or the uniform distribution, you can do whatever you want here. Of course, in practice, again, usually you are going to only bias in a finite range of values. Okay, you can do any, if you don't like Overdamp Langevin, you can do whatever you want. In fact, in molecular simulations, people have always, right from the initial paper, they have always been using the kinetic Langevin because that's, for physical reasons, that's what they want to use. Here, if you want to do kinetic PDMP, of course you can. The only thing is that you have to modify the gradient. And it's not only a question of playing with things. It can make sense, for instance, if you so if you're in your extended space, if you when you add a variable which is going to play the role of the collective variable, and if you do something kinetic, you have to give the distribution of the velocities, and so you can choose a mass, and you can choose a mass for the new fixed use particle, so the extended coordinate. You can choose, for instance, a very large mass, which is to say that it's going to move slowly. Okay, so maybe if it moves slowly, and if you have in mind that you are doing interacting particles, okay, so when you move the bias, when you move the reaction coordinate, so the extended reaction coordinates, all the particles have to know because they evolve with this value. Okay, so you have a problem of communication if you have many particles. So if you want to, they evolve in parallel, except that they have to communicate because they all have to use the same value for the extended coordinate. And so possibly it can make sense for numerical reasons to say, okay, all particles move with the kinetic Langevin, and then I have some random bounces involving the reaction coordinates, because now I can do that with thinning. And so maybe I can do several steps of the Euler scheme of the kinetic Langevin with the same reaction coordinate, and I just have to do communications when I propose an event which would be a change in the extended coordinate. Okay, so I'm not sure if I'm clear, but anyway, there could be reasons if you want to do other schemes, and anyway, you can do discrete time things. And also here I said, okay, we are going to enforce a biased target just by modifying the drift, but you can do other things. For instance, you can keep a non-biased dynamics, but now you add Metropolis Hastings reject with the biased target, and so you will have some acceptance which depends on the drift. And so also you can do birth and death selections if you have particles. So everybody moves, all particles move with an unbiased dynamics. Again, you can do that in parallel. And then at some point you stop everybody and you say, okay, and you do some, again, you compute some score depending on the target, the biased target, and then you kill some particles and you regenerate them on other particles. Thank you. In such a way that to target the correct bias. So okay, this you can do many things like that. Okay. Also, you don't have to target the gradient of the free energy. You can try to learn to estimate the energy, the free energy itself, because as we said, the free energy is just log of the marginal density. So it's like the log of an histogram. And so it's what is done in the adaptive biasing potential method, and it's also basically what is done in adaptive umbrella sampling or well-tempered metadynamics. So we have many names of the Wang-Landau algorithm, which can be somehow interpreted in this family when you choose the collective variable to be just the energy itself. Okay, so you have a lot of different things which somehow are all based. The common feature of all those guys is that they try to bias only in a low-dimensional manifold, which is basically, so at least in umbrella sampling and well-tempered dynamics, it's described by some collective variable. And okay, so I decided to present more with some details the ABF algorithm instead of those guys, because first I'm more used to it, so it's simpler for me, and also from okay. So I'm not going to say in practice which guy is better, okay, because I don't know. And usually when I read things about that, or when I discuss things about that, so for instance, Chris Schippo, who was in the references and who has worked a lot with this kind of thing, he was saying, okay, he's doing like a mix of metadynamics and ABF. So because somehow metadynamics, it's a strong bias, so it goes fastly. You escape from. It's okay. It's better to escape from a local well, but it's not good for the long time convergence. So you start by escaping with metadynamics, and then you go with ABF, which is more accurate. At least that was what I understood from our discussions. But at least from a mathematical point of view, there is something which is appealing about ABF, which is that you estimate the gradient of something. So if you estimate the gradient of something, of course, the something of which you are estimating the gradient is smooth. It's smooth because you are estimating its derivative. While if you're estimating this, okay, you're doing somehow independent estimation in each bin of your grid, and then you're taking the gradient of something a bit noisy. Of course, okay, you're differentiating some noise, which is possibly not very good. Did I want to say something else here? No. Anyway, no, there were questions or so. Yeah, and we have to be careful because, for instance, initially metadynamics have been introduced and was used, and everybody was very happy. It was super. And then some people realized that it was just wrong. I mean, okay, you get super fast something, and something is just not the number you want at the end. And okay, there was a belief that okay, the initial metadynamics was oscillating. It was never converging. Okay, because you were always adding the bias. Okay, the bias was always updated. And there was the belief that it was oscillating around the correct value. And so if you average, you would get the correct value. But okay, I think this is false, that it oscillates around the correct value. And it's, yeah. And so there is a well-tempered metadynamics, which looks like that. And somehow it's like putting this 1/t while it was not in the metadynamics. And so you get something reasonable. But okay, so you have to be careful with all these cooking recipes on the market. Anyway, here is another variation, which is interesting. Okay, so if you're in dimension larger than 1, I said that you use as a bias this. So this is the conditional expectation of a gradient, but it's not a gradient. Okay, this function as a function of y in dimension, it has no reason. It has no reason to be the gradient of something in dimension larger than 1 at least. And so what you can do is say, okay, my bias is not going to be this estimator, but of this average of the gradient, it's going to be some projection over a space of gradients. So that's called the Emmers projection. At least if you do the flat projection, so the projection with respect to the Lebesgue measure. So okay, you have a field. The force field, which given a vector give you a vector, and then you say, okay, I'm going to approximate it by the best gradient among, okay, let's say function in the H1 for this to be well defined. Anyway, okay, and so this is your, this can be your estimator. So this has been done in dimension 2, and it was observed that it was reducing the variance of the estimator, which is kinda to be expected because you are, okay, here you are estimating a vector field, which is a complicated object, and then you are projecting it on a smaller space, which is a space of gradients of functions. Okay, and not all vector fields are gradients of functions, and so by projecting you have a problem of dimension smaller, and so you have smaller variance of your estimator here. And so somehow a gradient, having a gradient is having the function b. Okay, so instead of having a vector field from Rn to Rn, you just have a function b from Rn to R, and so it's much somehow much simpler to do. Okay, what I wanted to, okay, so this is in dimension 2 or 3 maybe, not necessarily more because, okay, to do this problem. Okay, so if you look at the solution of that, this is the solution of a linear PDE. Okay, you just take the critical point of that, and this would be the Laplacian of B should be equal to divergence of F. Okay, and you solve that with your PD solver, the PD solver that you prefer. Okay, but then you have to compute this function F, which is here. So again, it's something you can do if you have a grid, but now something which makes more sense if you are in in larger dimension is to say that okay, remember gradient A is so it's a conditional expectation, and so it's a projection. It's the best approximation of remember, so this is a gradient B of y minus gradient y u of y z. Okay, when you are considering the measure mu. Okay, this is conditional expectations or projections in L2 space, but in L2 here in the probability measure. Okay, and so this somehow here we have done two different projections, one after the other. First, we have projected. We have taken the conditional expectation. So we have like considered the problem of finding the vector field which minimizes this, which turns out to be a gradient. Okay, and then we say, okay, but let's take a gradient. But then we could directly say, okay, I'm going to do that. And now you see that, okay, what is the difference here? So this is the this is this. Okay, so this is in R n plus p. Okay, let's write with so p of y, p of z given y. Okay, let's write it like that. P being mu. Okay, what do I want to say? Okay, so now if okay, you see that this is not natural. Okay, we have taken the conditional expectation with respect to mu with a vector field, but then we take the projection in the flat space. While what would make sense is to take expectation with respect to the marginal of y. Okay, because we would be really solving this. We would stay in the same scalar product. Okay, I don't know if I'm very clear. Okay, we could say. Gradient A is, okay, I don't know how to do it. Okay, let's say you have f, which is the conditional expectation of what we have here. Okay, what should be reasonable is to say, okay, I'm going to project it with respect to the law of y. So I want to minimize that because that would be my initial problem is exactly the solution of this full projection of. Okay, I have all functions. I have here okay, I have all functions which is RD. Here my space is the function which are y measurable. Vector field which are y measurable. Okay, this is this whole space. So I project my force on this, and then I project it on the space of gradient, and I get gradient A. Okay, so I'm doing two steps, but here in between I have changed the scalar product because the reason the scalar product for this, if you apply it to functions which are measurable, which for gradient vector form. Vector fields which are functions of y, you are taking taking the projection with respect to the marginal law of y and not the Lebesgue measure. Okay, so end of this discussion, I'm saying that it would be more natural to do that, and now you have a classical statistical regression. Okay, you have a sample of y's and of this. Okay, and you are saying, okay, I want to find a function which here is of a particular form because I want the gradient of something. Okay, in some space of function that I want. Okay, and now you can. okay, maybe some people here more than me know that we have ways to do to do regression. Why do I rate linear? Okay, linear if you want to. But anyway, we want to solve this problem with possibly a function which is more than the function y. This is a function of y. Okay. Possibly if the dimension of y is more than 2, people know how to do that in some. Okay, we have tools to infer functions in more than dimension 2 when they solve some when they minimize some empirical risk. Okay, and okay, so that's what and so. Okay, so it's a natural extension of projected ABF is say, okay, now my estimator is going to be taken as some the solution of some statistical regression given by this problem. And now I replace that by a sample, which is the sample I am constructing by the algorithm. Okay, this adaptive thing. Okay, and so first I said that having a gradient reduces the variance, and also it's important for re-rating because, okay, we are doing a biased Langevin diffusion, but now you have to re-rate, so the bias depends on time. So we have to unbias, okay, this is like the assumption that when you do the algorithm, somehow you believe that at time t you had reached the equilibrium of that guy, which of course is false, but you cannot do better than that. And if the drift is going to converge to something, so you are going indeed to sample this biased distribution. Okay, but now you have to reweight by the ratio between what you are sampling and what you want to sample. And what are you sampling when you do a Langevin dynamics and you add a drift f, which is a vector field? The answer is we have no idea. We have no idea if f is not the gradient of something, and if there is not some particular structure like we have some divergence-free drift or whatever. If we have a general vector field, we have absolutely no idea. We cannot have a closed formula for the density of the equilibrium of the Langevin dynamics with a vector field f, which is not the gradient. Okay, so now if we have a gradient, which is the case with projected ABF or the variation that I said here, we exactly know what we are supposed to sample with this fixed bias, and so we can reweight. Okay, and maybe that's a good time for a new break. So other questions on these last things? And so just teasing for the next session, because it was the discussion we had the first break. Okay, of course, the question is, that's all good, but all this depends on having collective variables. How do you get them? And so we'll see that over the recent years, people have asked the same question, and okay, and we'll see that in the next episode.
So 3:15, yeah, around 3:50.
No, I'll follow your schedule.